Well, hello and welcome to AMP1 Bio 211. And what we're doing now is we're looking at Chapter 2, the chemical level of organization. And remember, the best way, of course, to utilize these efforts here is to have read the textbook beforehand. Then you're going to come listen to these or listen in class and then go listen to these. But some mechanism where you find you're reading and you're thinking of questions as you're going along. And that's the ideal. You're coming to class prepared with questions of material that didn't make any sense to you. Okay, so let's get to work. At the beginning of Chapter 1, they show you the particle structure of all living organisms. This begins at the atomic level. And what we need to do is we need to entertain the idea that the atomic level, of course, is what's going to make up chemicals. And those chemicals are going to compose your body. And all body activities are chemical in nature. And they're governed by the fundamental laws of physics. Now, it doesn't mean you have to have taken a physics class. Okay, but it does mean that these are immutable. These things are not flexible to your whim and your will. You want to make sure you understand the concept of the chemistry itself and understand that essentially what we're doing is we are either building something, B-U-I-L-D, there's supposed to be a B there, B-U-I-L-D-I-N-G, or we are taking something apart, so we're deconstructing it. And the beautiful thing about the human body, and or for that matter, all living organisms, is that, it's going to be built around four basic chemicals: carbon, hydrogen, oxygen, and nitrogen. And these, when we assemble them, this is how we're going to build life itself. That makes up that 90-something% your textbook talks about. I think it's 96%. Okay? Equals 96% of all of the elements that make up your body. And there's a familiar theme as well, and that can be, when you think about the slide, this one here, how matter is organized. Well, elements are the addition and subtraction of the fundamental building blocks of matter. Okay, so we want to make sure all forms of matter are composed of chemical elements, which are substances that cannot be split into smaller substances. Well, what the frick does this mean? Well, this means that you understand that a certain number of protons, neutrons, and electrons are required to build every unique form of an element that we discuss inside of this class. Okay? And the description of these can be simplified for you into those chemical symbols that you learned back in chemistry class, but also I just gave to you like a moment ago as an example: carbon, hydrogen, oxygen, nitrogen. And there are many of these inside of your body. Obviously, you're made up of trillions and trillions of elements that are in transient states. Because you're alive, we build and we deconstruct things rapidly depending on the needs of your body. And in some extent, or to some extent, trace elements are going to be required for all of this to happen as well. Okay, so what is the structure of an atom? This is just review. An atom contains protons, which are positively charged, neutrons, which are neutral in charge, and the electrons, which fly around this thing. I draw it for you something like this. Here is a neutron, yay, and here is a proton, yay, and we're going to have one electron spinning around you like this, and one electron spinning around you like that. And if you change the numbers of these, we change everything. So if you change the numbers of protons, you change the number of neutrons, you change the number of electrons, and that's how you increase or decrease the complexity of the world that you see around you. Okay. Oops, I gotta get rid of the cartoon. So let's go here. What are the rules? Okay. This is sort of the fundamental pieces of information you'll have to know. Not only in this class, but, everywhere you go after this and you take some fundamental exam. The atomic number is the number of protons in the nucleus itself, whereas the mass number is the sum of its protons and its neutrons. And if you are looking at a mass number and you see that there are isotopes of it, naturally occurring isotopes, these are what are used to create that mass number. Example given inside your textbook here is hydrogen, carbon, nitrogen, and oxygen across the top here. And below here are some of the electrolytes you actually find inside of the body. And what I mean by that is these are ionizable, which means they are charged, which means we're going to regulate their movements, where we're going to use hydrogen, carbon, nitrogen, and oxygen to build everything. It's kind of cute the way they do this for you. We need iodide so that you can actually make signaling molecules inside of your body. If you have too much potassium inside of your body, it stops your heart along with everything else. And we need a constant charge difference of sodium across a membrane. And the funny thing is wherever sodium goes, chloride wants to follow. Now, this might be above or too much information at this point in time, but remember when you were 6 or 7 years old, just take a look at the cartoon and see the pattern. Okay? Because really that's what you want to see here. You want to see that there's a pattern. There's a certain number of protons, there's a certain number of electrons. You can do all the counting yourself and then move on, because it's not like we actually ever have you count this stuff. Okay? Get rid of the cartoon. That atomic mass, okay, is called a Dalton. I'm never going to ask you what a Dalton is. Go to a chemistry class if you want that. And the atomic mass is as close to the mass number of the most abundant isotope, because it's an average. And because the average for the most abundant is going to be the biggest number, well, guess what? Okay, so why do we care about this stuff? Well, we care for many reasons, but not the least of which is going to be, how do we actually use them? Because ions are elements that gave up or gained an electron, which means what we've actually done here is we've let you know that they've changed their reactivity. Okay, which means they're more capable of entering into chemical reactions, or we can use that charge energy to change an environment when we allow those ions to move into that space. And molecule, of course, is the atoms that share electrons, okay, when we put them together. And this would be, let's imagine we were building a water molecule. This is 1 oxygen and 2 hydrogen atoms, that are flying around this electronegatively charged element. And what you want to do is you want to see, well, hey, if we're going to build something with complexity, we now call it a molecule. In some instances, there are these things that are called free radicals, and we need free radicals. They're unstable and they're highly reactive, but they can become stable. Your body will do this to protect itself. But antioxidants are substances that are inactivated oxygen-derived free radicals, and which means inside of your body you have oxidants. Okay, Mother Nature uses oxygen to derive those free radicals. Okay, and inside your diet, in these days you're told, drink as many antioxidants as you can in the course of a day, your green teas and all that sort of stuff, right? Okay. Well, what they're doing is they're saying that if you have these oxygen-derived free radicals running around your body, they can wreak havoc. And in fact, they do. As we age, we have fewer and fewer antioxidants inside of our body. And that's one of the mechanisms by which we naturally age. How do we actually hold all of this together? Well, we do this by creating bonds. Okay, and we create bonds by undergoing chemical reactions. So we create these by making, or breaking interactions, between elements. And that's what a chemical bond is. And as fancy as that sounds, it's really not all that fancy. Okay? Because at the end of it, it's an observed frequency with which a chemical bond will be formed, and it's governed by the likelihood that the electron of one atom interacts with the electron of another atom to stabilize its outermost valence shell. Okay? So the reality is the way it works is you have two things next to one another, and their electrons will interact with one another, and if they create a stable state, they'll interact in such a way to create a chemical bond. Okay? So having said that, what type of bonds can be formed? Well, go back to your chemistry class. Remember, there are ionic bonds when an atom loses or gains a valence electron. Positively and negatively charged ions are attracted to one another. It's just the way the world, how do I say this without sounding pedantic? A fundamental observation in the world of physics is that if something is negatively charged, it is automatically and irreversibly attracted to something that's positively charged. It's not something you can ignore. So, because that's the basis of all interactions in our known universe, you have to understand that cations are positively charged ions that have given up one or more electrons. They're electron donors. And anions are negatively charged ions that have picked up one or more electrons. So this means it was given away, and that means these were taken, right? Yes, no, maybe? Okay, so, and that's why we simplify it. Ionic bonds, electrons are given up or taken. The example your textbook uses is kind of cute too, because it's sodium and chloride, where an electron from sodium is transferred over to chloride to make it stable, but it's given. So therefore, you now have the outer valence shells of sodium being stable and the outer valence shells of chloride being stable. And when you take away water, you actually see the ions that are formed here, meaning the crystal, as a result of the ions interacting with one another. That's going to be important when we think about how water actually works in a few minutes. Covalent bonds, well, these are a little bit different. Covalent bonds are common, and they are the strongest chemical bonds inside our body. Okay, so you think about what Mother Nature is doing. She's creating something that can't be broken apart easily, and you can actually have single, double, or triple covalent bonds by sharing 1, 2, or 3 pair of electrons. Covalent bonds may be polar or nonpolar, and nonpolar covalent bonds atoms share electrons equally. So it's the nonpolar covalent bond that does this. Polar covalent bonds, like water, okay, are unequal in their distribution. And I've drawn water for you several times on the board already, but you'll see what I mean when I draw it again in a moment. Here's some examples of a single bond, double bond, and a triple bond. So nitrogen atoms to give us the gas, N2, require that you actually share 1, 2, 3, 4, 5, 6 electrons between each of these nitrogen molecules, such that you end up, I should say nitrogen atoms, to give us a nitrogen molecule. Okay? So when you add them up, you now have something that's stable. The complexity, of course, can change here. This is a nonpolar interaction, which is equal. Here's methane gas, hydrogen, 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 and they're sharing the electrons 2 per as you go around to give you an octet rule being fulfilled here. But here's the water molecule I was telling you about a moment ago. Here's, and the way I've drawn it, of course, is that they will spend different times in different places, but hydrogen's electropositive, oxygen's electronegative, and even though they're attracted to one another, they're moving in an oblong or non-symmetrical manner. Okay, and that's going to be significant because polar covalent bonds, unequal sharing of electrons between those atoms, means that you can actually interact with other materials temporarily. Because remember, if you're an element and you have an electron and you're moving around, but you're still attached to something else, the interaction will be short-lived. Hydrogen bonds, they make up essentially most of the fundamental interactions we're going to consider inside of the human body, because temporarily they hold things in their 3-dimensional shape. Okay? But they are about 5% as strong as a covalent bond, okay? And they're used to establish links between molecules, different parts of very large molecules. And what we mean by this is, here's a pen. Let's imagine a molecule has this shape here. We're going to say that that's not functional. Okay? To make it functional, what we have to do is we have to now refold it properly. Okay? And we're going to hold the ends. And how can we hold the ends? We can do that by putting hydrogen bonding between them. And now, little dots I'm putting in between here. Right? I'm trying to put little dots for you guys in between here. And those would be the hydrogen bonds. And now it's in its 3-dimensional shape that will now allow it to be functional. So this is non-functional, NF. Okay. And this would be its functional shape. And it's in its functional shape because it has some hydrogen bonding here to hold it in that shape. You'll see it's a lot more complex than that, but generally speaking, if you get the idea, you can start to apply the idea. So let's take a look at some hydrogen bonds here. Inside your textbook, they have these. They are weak intermolecular bonds between molecules, and they help the three-dimensional shape given. Okay? And when we think about their role inside water, well, what they do is they actually create surface tension inside water, which is important when we think about how, say, your lungs work. Okay, so that's a pretty good place to stop for the first one here. So we'll pick up at the end of hydrogen bonds, moving our way into chemical reactions. Okay,